bird, the front brain has enlarged further. A bird is smarter than a reptile. In the first mammals, the growth of the front brain and intelligence continued, until in humans, the crinkled surface of the front brain seems to have taken over entirely. But hidden inside and below, we still have our ancient fishy brain carrying out its age-old functions. These nether regions of the brain keep our hearts beating and our lungs breathing. The cauliflower-shaped cerebellum keeps our bodies in balance. The human cerebellum is the most complex in the animal kingdom, possibly because it's more difficult to balance on 2 legs than on 4. This early part of the brain has a primitive beauty all its own. Without the cerebellum, we'd have to concentrate on standing upright and taking every step. From its primitive base upwards, the human brain has successive layers of intricate connections and staggering complexity. In these layers is hidden everything that makes us individuals: emotions, memories, aspirations, and thoughts. The human brain has reached its present complexity and size in only 5 million years since the human lineage split from the chimpanzee. The story of the brain's evolution is revealed by changes in the skull. A modern chimpanzee has a brain only slightly smaller than one of our possible ancestors, Australopithecus africanus, who lived 3 million years ago. 2 million years ago, a larger-brained early human emerged. These people made the first tools. Dating back 500,000 years, this human skull housed a brain twice as large as the early Australopithecus. Homo erectus had mastered the art of using fire. The human brain reached its present size 130,000 years ago. But it took another 100,000 years to reach a mental capacity similar to ours. A child from 35,000 years ago could easily learn all the skills needed to survive in present-day society.
Are the cells excel?
The human characteristics that evolved then, self-expression and curiosity, are still the cornerstones of society today.
Although this, I'm going to keep cruising around here for you because this is...
The number of nerve cells in the brain has multiplied immensely over the past few million years. The brain was in danger of outgrowing the skull, but it was saved by a clever piece of geometry. The cells we use to think lie on the surface of the brain, in a layer just 1/8 of an inch thick, the cortex. And a large surface can be stuffed into a small volume by crumpling it up. Like a sheet of paper, the cortex has crumpled into fissures and grooves. If we smoothed out the crinkles, the cortex would be the size of a pillowcase. With these intricate folds, we far outdistance the thinking power of even the largest animal brain. The nerve cells in the cortex do everything that's unique to humans. To make decisions, to voice opinions, to interpret what we see and hear, and to understand it. The crumpled cortex forms 2 distinct hemispheres, each filled with bundles of nerves. The 2 halves have different ways of interpreting the world. The left hemisphere thinks in words, while the right half thinks in images and feelings. The nerves exchange information through a dense band at the base of the brain. Every point in the right hemisphere is connected to an exact mirror image point in the left hemisphere. If the word water appears here in the left hemisphere, then just here, the right hemisphere has an image of water. To prevent any argument within the brain, one hemisphere, almost always the left, makes the ultimate decisions. When it comes to controlling the muscles, each hemisphere is responsible for one side of the body, all the way from the feet and legs to the hands and eyes. But the lines of command cross over. The left side of the body is connected to the brain's right hemisphere, while sensations from the right side of your body end up in the left hemisphere. The most sensitive regions command a disproportionate number of nerve cells in the brain's feeling center, called the sensory cortex. This weird figure shows how your brain feels your body to be. Highly sensitive parts loom large in the brain's view of the body. The lips look huge because they're extremely sensitive and ideal for displaying our feelings. Children instinctively use their lips to explore the world around them. The ball stimulates the nerves in his lips, sending signals to this very specific part of the brain. A different part of the sensory cortex lights up when you touch something with your right index finger. The hand is packed with nerve endings, so we feel it to be much larger than life. The thumb is biggest of all. It can discriminate the finest details by touch. The entire back stimulates fewer nerve cells in the sensory cortex than the palm of your hand. A second figure shows how much of the brain is devoted to controlling our bodies. His largest parts have many nerve cells in charge of finely tuned muscles. The two distorted figures have much in common. Parts of the body sensitive to touch generally need the finest control. From birth, our nerves can feel sensations, but it takes time and patience to control our muscles properly. Among the first we master are the facial muscles. A baby can express emotions with a smile or a frown from a very early age. Our facial expressions acquire more finesse as our muscles and nervous system become more mature. The expressive lips need fine control to convey speech and emotions. In the brain's view, they are enormous. The hands are packed with precision muscles. The huge amount of brain devoted to the hand has been vital for our evolution from our clumsy ancestors, and it's led to some of our greatest cultural achievements.
If you want to try and look for... Actually, we do have a...
To monitor our muscles, we rely on our vigilant sense organs. Each is connected to its own region of the brain's cortex. The eyes send signals to the back of the brain, along nerves that cross over on the way. Where we see the world is strangely furthest from the eyes themselves. When you see something, electrical signals race along these pale nerve bundles. They carry coded messages through the brain's massive hemispheres to the back of the cortex. This scan shows electrical activity in the part of the brain where the messages are received. The ear keeps us in touch with every sound and with messages from our fellow human beings. Sounds are amplified and detected by a natural microphone. Its signals, more sensibly, are analyzed in a region of the brain right next to the ear. Smells are conveyed by invisible molecules to the back of the nose. They trigger nerves that fire straight into the depths of the brain, where our emotions reside. That's why smells can trigger long-lost feelings and other memories. Here, a sniff of perfume lights up several parts of the brain. The visual region at the lower right is recalling a view associated with the smell. The unconscious pathways that link our senses are still largely unexplored, and we don't understand how the cortex ties together its scattered responses to our different senses to create a seamless image of the world around us. Most things we do involve almost every part of the brain.
Tell me all the meanings of law in English.
Even something apparently as simple as answering a question.
Yes?
We must hear the words, understand them, draw on our memories, and then voice the answer.
She? Anybody help?
Because it reinforces particular pathways through the brain, language has molded the very way we think. This area organizes our thoughts according to the rules of grammar. It sends signals to the region which coordinates our breathing, vocal cords, tongue, and lips to allow us to speak.
Conmigo.
Muy bien, perfecto. Now we're on a conjugation round.
Language helps us to learn new facts and new ideas. But we can't recall everything we were taught at high school. The brain is selective, choosing what seems to be important, and it stores information in two stages. First is short-term memory. Hear a new word, and you can recall it for a few seconds, but it will quickly fade unless it's filed in the long-term memory.
All has to be right for the point. Who shall I choose? Desesperados? Corey.
Traduzco, traduces, traduce.
To retain what you've learned, the brain must build up permanent new connections between its nerves. The actual structure of the brain changes subtly each time we commit a new fact to our long-term memory. New links are forged throughout the brain. But it's still a mystery how we can recall these dispersed memories at will.
Yours, Mr. Johnson.
With constant repetition, memories become more deeply ingrained. The brain can teach itself by repeating words and facts mentally. Remarkably, the technique also works for physical skills.
Hey, Mr. Johnson, Mrs. Johnson, yours. Su, su. Perfecto.
The human brain is our most wonderful and our most mysterious organ. Scientists have yet to learn the function of every fold and crease, and how this mass of nerve cells creates intelligence, consciousness, and self-awareness. A computer that can think, let alone be aware of itself, is still far off in the realms of science fiction. Yet each one of us contains a far more powerful computer than any space-age instrument. The human brain has the ingenuity to take us to the furthest corners of the earth and beyond. Its mental reach knows no limit. With our flexible brain, we can look beyond our own world and contemplate the infinite.
The human body is a finely tuned machine. All humans are built to the same blueprint of muscle and bone. But we can use them to perform amazingly different tasks. With speed and strength, perfect control, and exquisite balance, our bodies are miracles of design evolution. Witness the power of muscle and bone, next on Body Atlas. Bobby Thatcher is about to take the plunge. He's an Olympic hopeful in rowing, and this early morning workout is just one part of his intense training program. To make the team, Bobby must continually improve his performance. Understanding how his body works gives him the edge he needs to outpace the competition. In his case, knowledge is truly power. Today, he'll be racing the clock as he prepares for upcoming time trials. Rowing is a showcase for the human machine. Bobby's powerful strokes coordinate perfectly with his well-trained muscles. A heat-sensitive camera reveals the inner secrets of the biological engine powering the boat. Muscular pistons connect bone levers that are pivoted at joints and greased with natural lubricants. The muscles are driven by sugar dissolved in the bloodstream. Human power is transferred to an artificial lever. The carbon fiber ore pivots on a steel swivel. Smoothly and efficiently, Bobby's internal fuel supply is converted to the force on the ore blade that drives him on. But to win, Bobby must perfect every aspect of the boat's human engine.
Breathe normally, so 3 breaths.
At an Olympic training laboratory, Bobby tests his lung power. He needs a plentiful supply of oxygen to burn the fuel in his muscles.
Hand fast, hard fast. Keep driving. And in. That's it.
His lung capacity is amazing. He can breathe nearly 2 gallons of air in one breath. Bobby regulates his breathing carefully as he warms up. Gentle exercise increases the blood flow through the body. The muscles tune up to use oxygen more efficiently. The energy Bobby will use is actually already stored in his tissues as a form of sugar called glycogen. As his muscles burn more sugar, his blood carries the extra heat to his skin to be radiated away. The tiny blood vessels in his face dilate quickly to help cool the blood.
Okay, get ready for this, please.
It's time to test Bobby's training. His body is primed, both on the water starting line and on a dry run in the lab.
Set, go!
Go.
Hours in the lab have taught Bobby how to get the best out of his body. He has rehearsed the grueling race under intense scrutiny.
That's it, nice and sharp off, well done.
Bobby must use his limited reserves of energy wisely. Only 1/4 of the chemical energy in his muscles' fuel is turned into useful power. 3/4 is wasted as heat. Human muscle has an efficiency of 25%, the same as a modern automobile engine. But no one can match the huge energy resources of machines. A power graph demonstrates what happens. The first blips show Bobby's initial burst of energy, but his muscles can't keep that pace up for the whole race. He must drop his stroke to a less hectic cruise for the next few minutes. At this slower pace, the human engine is rated at 1/2 horsepower. At peak performance, it can work to 4.5 horsepower. It would take 50 athletes like Bobby to power the average car. Bobby's intensive training is taking his body to new heights. But like any efficient machine, the human body needs a solid framework. A 9-week-old fetus appears to have a full complement of bones, but actually, it's a framework of tough, flexible cartilage. True bones will form around it later. This ingenious bit of evolution allows the baby's skeleton to withstand knocks and its skull to be compressed slightly during birth. The skull plates won't fully connect for 18 months, allowing the baby's brain to grow to full size. Infants are born with 350 bones, 150 more than an adult has. Many of them fuse together during childhood, and by age 25, the average adult is down to 206. This gives us fewer but stronger bones for adult life. Bones are among nature's most perfect creations. They are light, but incredibly strong. Ounce for ounce, they can withstand 4 times the weight resisted by reinforced concrete. Underneath our muscular coats, bones shape our bodies. They support us and give our muscles leverage. Our skeleton weighs about 30 pounds. That's less than 20% of our body weight. The shape of each bone is highly specialized, yet the complex structure of the limbs makes them immensely flexible and versatile. The arms are supported by a bony framework across the shoulders, which is only loosely connected to the rest of the skeleton. The shoulder blades are not attached to the rib cage underneath, allowing the arms a wide range of movement. Inside the bones, a mysterious world emerges. 1/3 of a bone's weight is made of living tissue, linked by a microscopic network of blood vessels and nerves. The center of some bones is filled with marrow, which manufactures blood cells. This microscopic architecture lies within many of our bones. Its open structure combines strength with lightness. Bones are not permanent. The minerals that make up the hard part of the bone, calcium and phosphorus, gradually dissolve and are carried away in the bloodstream. New bone is built up from minerals supplied by blood vessels that travel through tiny canals in the bone. As a result, our skeletons are replaced every 2 years. The crystals of new bone are layered to provide strength, similar to the construction of carbon fiber in an ore. Like the ore, the bone levers in the human body must work against a pivot or a joint. Of all the joints in the human body, the knee is the most complex. It must flex while carrying heavy loads. The kneecap allows the muscles to pull strongly around the bent joint. To keep friction to a minimum, the bones are separated by a soft pad. It's filled with a syrupy natural lubricant called synovial fluid. Without their well-oiled joints, our bodies would move as stiffly as robots. Joints and bones work together to amplify the motion of our muscles. The pivot point of the elbow magnifies the movement of the bicep muscle in the upper arm. This wide hand swing requires only a 1-inch contraction of the biceps. But the human hand is probably the most amazing piece of bioengineering. It sets us apart from most of the animal kingdom. The thumb faces the fingertips, providing a strong yet sensitive grip. The 3 longest fingers are operated by muscles in the forearm. Their power is transmitted by long tendons. The fragile finger bones are built for delicate work, not strength, and the joints are correspondingly refined. In contrast, the massive backbone has the weight of the upper body to support. It also provides armor for the spinal cord, the superhighway of nerves that carries messages between the brain and the rest of the body. "31 pairs of nerves fan out from the spinal cord. Towards the base of the backbone is a bundle of separate nerves called the horse's tail. The end portion of the backbone, the coccyx, has no nerves. It's the evolutionary remnant of a tail. This isn't a dinosaur's back. It's actually a human spine. These protrusions anchor the muscles that hold the human backbone together. The 24 individual bones, the vertebrae, are separated by shock-absorbing discs. Our body weight compresses the discs when we stand. We shrink by a fraction of an inch during the day, but we regain it during sleep. Our bony frame is held up by our legs, the strongest bones in the body. They can support up to 1 ton of weight. The foot bones are an exact counterpart to the bones of the hand, but shaped for different purposes. Stubby toes provide springiness. Arched bones spread the weight of the body, which is transmitted through the massive heel bone. The skeleton also provides protection for the heart, the lungs, and other vulnerable organs inside the body. The ribs help to spread the load. The skull is designed like a helmet to protect the brain, but sometimes it meets